Hello, thank you for this opportunity to present our work. I am Inna Gerlovina, and I'm going to be talking today about our genetic distance method with Dcifer. First, a little bit about motivation. Consider genetic distance between two parasite strains. It can be well defined in terms of identity by descent. However, when we have two infections, possibly polyclonal, that is not as straightforward to define and hard to estimate. And yet it is the distance between infections that plays a central role in inferring transmission. So say we have data with polyclonal and monoclonal samples. What are we going to do? There are various approaches that can and were taken. First, we know how to do the distance between monoclonal samples, and we can get there by either filtering, removing polyclonal samples, which introduces bias, or reduce polyclonal samples to monoclonal, and that also brings up some noise. Another direction is that we can try to infer individual haplotypes within polyclonal samples with phasing. Again, introduces uncertainty and computationally very intensive. Here I want to mention gold standard for these single cell whole genome sequencing. Another approach would be to use some identity by state metric, which doesn't care if it's monoclonal or polyclonal, comes with its own shortcomings, not easily interpretable, lower power to detect lower degrees of relatedness, sensitive to complexity of infection. So we would like to have a method that is accurate and interpretable, computationally efficient, and can handle biallelic SNPs or multi-allelic data. I'm going to start identity by descent with just a pair of strains. So IBD gets to the question of interest. And a quick reminder is that two alleles could be the same, either by chance or by descent. And descent is what we are interested in. And it also allows for statistical framework with models, parameters, estimators, and all the inference and all the good stuff. For model, again, between two pairs of strains, we consider IBD, binary, yes or no, across loci, and they are IID, Bernoulli distributed random variables with a parameter R. And this parameter R is what we call relatedness, and this is what we would like to estimate. For a pair of polyclonal infections, consider these are two infections, and each horizontal line is a strain. And at this point, we are only considering between host pairs of strains. And I will be, so essentially we're constraining our model space, and I can elaborate more during Q&A session. And Dcifer, what it does, it estimates parameters, these R's, of a joint distribution of IBD, and there are 3 of them in our example, and it is a maximum likelihood estimator. I'm not going to go over likelihood in this talk, but it's here, so if anybody wants to look at it more closely, I will be very happy to answer any questions. The one thing that I want to point out is that what would be handled by phasing, in likelihood, we approach it with combinatorics. Now, getting to simulations, we compare different panels and also compare with IBS similarity metric. First, let's look at the density of sampling distributions for Dcifer and IBS. Dcifer is on the top, IBS is on the bottom, and this goes across various COIs, complexity of infection. So we can see that IBS metric is quite biased, and there is not that much separation between two different R's. So I should point out that colors represent different true values of this relatedness parameter. And yeah, Dcifer is doing much better in both regards. This was simulated without errors, and if we do include genotyping errors, we see the similar picture. Now the parameters are a little bit underestimated due to the fact that those genotyping error break up that relatedness between two samples a little bit. Okay, and now we compare the power at given false positive rates of 0.05. The colors here represent different values, again, of true values of the parameter, starting from 1/16 and going to half. Dotted line is IBS metric, solid line is Dcifer, and x-axis is different panels. So 23 SNPs, 101 SNPs, and then microhaplotypes going from 91 to 910. And so we can say that, of course, as the number of loci increases, the power is increasing as well. And Dcifer has much higher power than, we need to look at the same color, than IBS metric. And of course, when R goes up, it's easier, the power goes up as well. We can also look at the same picture across different complexity of infections, starting from 1 in X, 1 in Y, and 5. Here we can see similar picture, and of course, as complexity of infection increases, the power decreases somewhat, but Dcifer is still doing quite well and outperforming IBS metric. So now we get to the territory where we cannot compare it to IBS because IBS cannot deal with that. So we come to inference, and Dcifer can provide confidence intervals based on likelihood ratio statistic. And here the x-axis, this is COI, different panels are COI, different plots. X-axis is the true R here, and on the y-axis, we essentially have this confidence interval. For 0, it goes from 0 to different values, depending on the panel here. So for a different number of loci, not surprisingly, the lower the number of loci, the higher is confidence interval. You can see it in the color. And for 910 loci, the confidence interval is quite tight. Another thing that IBS cannot do is estimate various multiple pairs of strains. And so with Dcifer, individual R's are not always very accurately estimated. However, the sum of them is estimated really well. And this is a likelihood surface that kind of illustrates that. The red is the truth, blue is estimation, and the blue line is the sum. And finally, we come to data analysis. In Mozambique, patients from 2 health facilities in Maputo and in Inhambane provinces, each square represents a pair of samples. There's 63 samples. Lower left matrix is IBS, and upper right is Dcifer. The color represents R, the value of estimated R, ranging from 0 to 1, and the darker is 1. These are ones, I believe. And finally, the highlighting shows pairs that were determined significant, again, by this likelihood ratio based method. And finally, a couple words about calculation time. So example, for 1,000 samples, it takes about an hour. And for 91 loci, and the time for number of loci is linear. Some of the future directions for this method, we would like to try and incorporate errors in the model, Also, this will be quite easy, develop direct estimator for the sum of R's and work more on inference. And finally, I would like to thank all the people and organizations who helped with this project. Thank you very much.